All right, let's dive right into this explainer. Today, we're taking a look under the hood at the absolute heavyweight champions of the electronics world, BJTs and MOSFETs. If you've ever found yourself wondering what's actually happening inside the silicon of your laptop or inside the amp of your home sound system, you are exactly in the right place. But before we meet the contenders, think about this for a second. How exactly do you control massive amounts of electricity using almost none? I mean, how does a tiny component with literally zero moving parts act like a heavy-duty mechanical relay? Essentially, we're talking about building an electrical valve, one that can seamlessly switch or amplify current without any physical wear and tear. So here's our game plan for today. First, we'll look at the tiny electronic valve itself, then break down the current-controlling BJT, shift over to the voltage-controlling MOSFET, put them head-to-head in a showdown, and finally, look at how they power the real world. All right, kicking things off with Section 1, the tiny electronic valve, relays without moving parts. Here's the absolute crucial thing you've got to keep in mind. Whether we're talking about a BJT or a MOSFET, they both do the exact same core job. They take a tiny electrical input and they use it to boss around a much larger electrical output. They are the ultimate power brokers. Whether they're snapping zeros and ones on and off billions of times a second for a CPU, or acting like an adjustable volume knob to smoothly boost a weak audio signal, they are the foundational building blocks of literally all modern tech. Moving right along to Section 2, BJT, the current controller. That's the bipolar junction transistor. So let's meet contender number 1, the BJT. It's got 3 legs, the base, the collector, and the emitter. To really wrap our heads around how it works, it helps to think of water flowing through pipes. Imagine the main water pipe is the path from the collector down to the emitter. Now, see that smaller tube acting on the valve? That's the base. If you trickle just a tiny bit of current into that base, it physically pushes open the main valve, letting a massive, rushing wave of current travel from the collector straight through to the emitter. And that brings us to a super important concept, gain. You'll usually see it listed as beta or HFE on a datasheet. Think of this as the transistor's magic multiplier. For a typical general-purpose BJT, injecting just 0.1 milliamps of current into the base might allow 10 milliamps of main current to flow. That means it's amplifying your input by 100 times. It's a completely direct proportional relationship.
Well, actually, scratch that. There is a slight catch here. You can't just push any random amount of current in and expect it to work. You've got to overcome a forward bias voltage drop of about 0.7 volts across that base emitter junction. It acts just like a standard diode. If you don't hit that 0.7 volt mark, that valve stays firmly shut and you get absolutely no current.
Okay, but what if we completely flip the script on how we control this valve? We're moving away from the strictly current-controlled BJT over to a totally different beast, the voltage-controlled MOSFET. This is a massive paradigm shift. Which brings us to Section 3, MOSFET, the voltage controller. That stands for Metal Oxide Semiconductor Field Effect Transistor. Quite a mouthful. Meet the MOSFET. Instead of a base, collector, and emitter, we've got a source, a gate, and a drain, and the physics happening inside are entirely different. Notice how the gate terminal is literally electrically insulated from the rest of the component by a crazy thin layer of oxide? Because of that insulation, the gate draws virtually zero continuous current. Zero! Instead, when you apply a voltage to it, it generates an electric field that reaches across the insulator to attract or repel charge carriers. It literally creates a conductive channel using a force field. And since that insulated gate acts incredibly similarly to a tiny capacitor, it really doesn't care about a continuous flow of current. You just have to hit a specific target called the threshold voltage. The split second you apply a voltage higher than that threshold, bam! The transistor snaps on, resistance drops to practically nothing, and massive current flows right through the main circuit. All right, Section 4, the transistor showdown, head-to-head comparison. We've seen the internal physics, so now it's time for the main event. We are putting them head to head. You've really got to consider these trade-offs. Look at power use and heat. BJTs need a constant flow of base current just to stay awake, meaning they chew up more power and get pretty hot under load. MOSFETs, on the other hand, are incredibly fast, and because of that insulated gate, they draw near zero continuous current, which keeps them incredibly power efficient and way cooler. So, who wins? Well, it completely depends on the arena. Because a BJT's output current is totally proportional to its input, it gives you this highly predictable, smooth, steady flow. That makes it the undisputed king for smoothly amplifying continuous analog signals. But if you need lightning-fast switching with practically no wasted power, the MOSFET absolutely dominates the digital world of ones and zeros. Let's make this practical in Section 5, Powering the Real World. Let's take all this theory out of the textbook and onto the breadboard. If you're working with analog signals, say you're building a sweet, high-fidelity audio amplifier for your living room, the BJT is exactly what you need. Its linear, high-gain nature reproduces sound waves beautifully. They're also fantastic in sensor circuits that need to gently, dynamically react to things like changing light or heat. On the flip side, what if you're building a super high-efficiency power supply or driving a beefy DC motor with an Arduino? You want the MOSFET, hands down. They're the absolute backbone of your phone chargers, your computer processors, and super bright LED drivers purely because they can switch heavy loads on and off instantly without turning all that precious power into wasted heat. So here is your cheat sheet for choosing. Step 1. Identify if you're working with an analog signal or a digital switch. Step 2. Figure out how sensitive your project is to power loss and heat. Step 3, make your choice. Oh, and here's a really cool pro tip. In advanced power electronics, you don't always have to choose just one. You can actually combine them in a single circuit to get the ultra-smooth gain of the BJT alongside the blazing fast switching of the MOSFET. Best of both worlds. At the end of the day, despite the crazy differences in their physics, one running on current, the other running on a voltage force field, they're executing the exact same mission. As one of our sources perfectly put it, you can really just think of them as slightly different flavors of the exact same thing. They're both just using a little bit of electricity to control a whole lot of electricity. So now that you truly understand what's happening under the hood of the current-hungry BJT and the hyper-efficient MOSFET, which one of these heavyweight champions is going to be sitting on your breadboard tomorrow?